quantum number. The numbers, which identify the state of an electron, specify the energy associated with it, and its location around the nucleus, are called quantum numbers. These numbers are used to designate and distinguish electrons in atomic orbitals. There are 4 quantum numbers: principal quantum number, n; Azimuthal quantum number, L; magnetic quantum number, m; and spin quantum number, s. An atomic orbital can be completely described in terms of a set of 3 quantum numbers, n, l, m. These quantum numbers partly describe an electron in a particular orbital. In order to specify an electron in an atom completely, a 4th quantum number called spin quantum number, s, has been introduced. An electron in an atom can be fully described in terms of a set of 4 quantum number, n, l, m, s. These numbers designate and distinguish various atomic orbitals and electrons present in an atom, and are called quantum numbers. Difference between an orbit and an orbital. 1. It is well-defined circular path around the nucleus, in which electrons revolve, according to Bohr's model of an atom. 1. It is a 3-dimensional space around the nucleus, in which the probability of finding an electron is maximum. This is in accordance with quantum mechanical model of atom. 2. An orbit can accommodate 2 n square electrons, where n represents the number of orbit. 2. An orbital can accommodate a maximum of 2 electrons only. 3. The revolution of electron in an orbit is against the Heisenberg's uncertainty principle. 3. Concept of orbital is in accordance with the uncertainty principle. 4. Orbits are circular. 4. The probability distribution of charge cloud in different orbitals is different. This gives them different shapes. 5. Orbits are non-directional. 5. Except s-orbital, all other orbitals are directional in nature. Principal quantum number, n. This number represents the main shell to which the electron belongs. It defines the distance of electron from the nucleus and its energy level. It is designated by n. It has the values n is equal to 1, 2, 3, 4, 5, 6, 7. These levels are also represented by the letters K, L, M, N, etc. The first energy level, n is equal to 1, is nearest to the nucleus, and has the least energy. The energy of the main shell increase as the value of n increase. Each main shell contains a maximum of 2 electrons. Thus, K shell, n is equal to 1, contains a maximum of 2 electrons. L shell, n is equal to 2, contains maximum of 8 electrons. M shell, n is equal to 3, contains a maximum of 18 electrons, etc. Principal quantum number provides the following information. 1. the principal shell, to which electron belongs. 2. The energy of the principal shell. For example, for hydrogen, En is equal to -1 upon 4 pi epsilon 0, the whole square, into 2 pi square, me, raised to 4, z square, upon n square, h square, is equal to -1312 z square, upon n square, kilojoule per moles. Azimuthal quantum number. Azimuthal quantum number is also called secondary, subsidiary, orbital, or angular momentum quantum number. It is represented by letter L. This represents the subshell, to which the electron belongs. It defines the shape of the orbital occupied by the electron, and the angular momentum of the electron. Its values depend upon the value of principal quantum number, n. It can have only positive values, between 0 and n-1, where n is the principal quantum number. Thus, the permissible values of L are 0, 1, 2, and so on, up to n-1. This quantum number provides the following information. 1. The subshell, in which electron is present. A principal shell in an atom is supposed to be composed of several sublevels, known as subshells. These subshells are represented by letter S, P, D, F. The letters S, P, D, F are derived from the terms sharp, principal, diffused, and fundamental. These terms are used in spectroscopy to describe the nature of spectral line present in the emission spectrum of atom. The designation of subshells in terms of the values of L is given in this table. The value of L is 0, the subshell to which electron belongs is S. If the value of L is 1, the subshell to which electron belongs is P. If the value of L is 2, the subshell to which electron belongs is D. And, if the value of L is 3, the subshell to which electron belongs is F. Number of subshells present in a principal shell. The values L depends upon the value of n. The azimuthal quantum number signifies the number of subshells which a principal shell can possess. It is illustrated in this table. Principal shell, value of n, permissible value of L, possible subshell, number of subshell in shell. Principal shell is K. Here, value of n is 1. Permissible value of K is 0. Possible subshell is S, and number of subshell in shell, 1. Principal shell is L. Here, value of n is 2. Permissible value of L is 0, 1. Possible subshell is S, P, and number of subshell in shell, 2. Principal shell is M. Here, value of n is 3. Permissible value of M is 0, 1, 2. Possible subshell is S, P, D, and number of subshell in shell, 3. Principal shell is N. Here, value of n is 4. Permissible value of n is 0, 1, 2, 3. Possible subshell is S, P, D, F, and number of subshell in shell, 4. It may be noted that the total number of subshells present in a principal shell is numerically equal to value of principal quantum number, n, of the shell under consideration. The subshells of a particular shell are specified by putting the value of n before the symbol of subshell. For example, S subshell of K shell is represented as 1s, while S shell of L shell n is equal to 2 is represented as 2s. Thus, n is equal to 3, and L is equal to 0, we have 3s subshell. N is equal to 3, and L is equal to 1, we have 3p subshell. N is equal to 4, and L is equal to 2, we have 4d subshell. The shape of subshell. The azimuthal quantum number, L, is responsible for particular shape of particular shell, because it defines the spatial distribution of the electron cloud around the nucleus. The angular momentum of the electron. The quantum number, L, is used to calculate the angular momentum of an electron in a particular subshell. The orbital angular momentum, L, of an electron in a subshell, with azimuthal quantum number, L, is given by L is equal to h, upon 2 pi into square root of L into bracket, L plus 1. Each subshell contains a maximum of 2 into bracket 2 liters plus 1 electrons. Thus, s-orbital contains a maximum of 2 electrons, p-orbital contains 6 electrons, d-orbital will contain maximum 10, and f-orbital will have maximum 14 electrons. Magnetic quantum number, m. This quantum number is used to explain Zeeman effect. It is represented by letter m. The values of m are governed by value of L. It can have any integral value between minus L and plus L through 0. M is equal to minus L, so on, up to minus 2, minus 1, 0, plus 1, plus 2 and so on, up to plus L. Thus, for a given value of L, M will have 2 L plus 1 values. This number is also referred to as orientation quantum number, because it gives the distribution of electron cloud in space around the nucleus. A subshell in an atom is supposed to be composed of several orbitals, or subshells. The magnetic quantum number, m, tells to which orbital an electron belongs. It also to the number of orbitals, which corresponds to a particular shell. For example, S subshell. L is equal to 0, therefore, M is equal to 0. This implies that S subshell contains only one orbital. Because we have only one value of M orbital contained in S subshell is called s-orbital. P subshell. L is equal to 1, in this case, M can have 3 permissible values plus 1, 0, and minus 1. Thus, a p subshell contains 3 orbitals. They are designated as px, py, pz, where subscripts x, y, z refer to coordinate axes. Thus, p orbitals possess different orientation in space. Px orbitals is oriented along x-axis by px along y-axis and pz along z-axis. However, in the absence of magnetic field, all the 3 p orbitals are equivalent in energy and are said to be threefold degenerate, or triply degenerate. In the presence of magnetic field, they acquire different energies, and their degeneracy is removed. C. For d subshell, L is equal to 2. Hence, the corresponding values of magnetic quantum number M will be +2, +1, 0, -1, -2. Thus, d subshell possesses 5 orientations in space, that is, d subshell contains 5 d-orbitals. These are designated as dxy, dyz, dzx, dx square, minus y square, and dz square. The first 3 d-orbitals dxy, dyz, dzx, are planar orbitals, and possess electron clouds, in the planes specified, as subscripts in their symbols. dx square, minus y square, and dz square, are axial orbitals. The former possesses electron cloud density at the intersection of x and y axes, while the latter along the z-axis. In the absence of magnetic field, these orbitals are equivalent in energy, and are said to be fivefold degenerate. D. For F subshell, L is equal to 3. Therefore, permissible values of M are +3, +2, 0, -1, -2, -3. Thus, F subshell possess 7 orientation in space, that is, F subshell contains 7 orbitals. F orbitals are fold degenerated, and are quite complicated in shape and designation. Spin quantum number, S. This quantum number is represented by S, and it accounts for the spin of electron. Since an electron can spin clockwise or anti-clockwise in 2 opposite directions, there are 2 possible values of S that are equal and opposite. The probability of rotation in one direction is only half. Therefore, the spin quantum number can have only 2 values, +half and -half. For clockwise spin value is +half, and for anti-clockwise spin value is -half. The spin of electron is also represented by arrow. A vertical arrow pointing upwards represents clockwise spin, while a vertical arrow pointing downwards represents anti-clockwise spin. Two electrons with the same sign of the spin quantum number are said to have parallel spins, while those having opposite signs of the spin quantum number are said to have opposite spins, or anti-parallel spin, or paired up spins. Since spinning charge is associated with a magnetic field, an electron must have a magnetic moment associated with it. S-orbital. For orbital L is equal to 0, for L is equal to 0, M is equal to 0. This shows that s-orbitals have only one orientation. They are spherically symmetrical about the nucleus. For each value of principal quantum number, n, there is only one orientation. For L is equal to 0, that is, s-orbital, there is only one s-orbital, for given n. For s-orbitals, there is only one orientation, it is spherically symmetrical about the nucleus. there is only one symmetrical orbital for each value of n, whose radius depends upon the value of n. The size of an orbital depends upon the value of n. As the value of n increase, the size of the orbital increase. 2s orbital is bigger than 1s. 3s is bigger than 2s. In between 1s and 2s, there is a region where probability of finding the electron is 0. It is called as node. P orbital. For p orbital, L is equal to 1, M is equal to +1, 0, -1. P orbitals have 3 orientation. Each orbital consists of 2 lobes. The 2 lobes are separated by a plane having 0 electron density. Such a plane is called nodal plane. There are 3 p orbitals, and are designated as px, py, pz. They are perpendicular to each other, and oriented along x, y, and z axes respectively in space. They are equivalent in energy, in the absence of magnetic field. D orbital. For d orbitals, L is equal to 2, M is equal to +2, +1, 0, -1, -2. D orbitals have 5 orientation. They are designated as dxy, dyz, d²y², and dz². They all are equivalent in energy, in the absence of magnetic field. The first 3 have double dumbbell shape, in xy, yz, and xz plane, respectively. The d²y² is also dumbbell-shaped, with a donut-shaped ring of high electron density around the nucleus in xy plane. dz² is also dumbbell-shaped, with a donut-shaped ring of high electron density. Shape of d orbitals are shown. Spherical, or radial nodes, and nodal planes. A spherical surface, within an orbital, on which the probability of finding the electron is 0, is called spherical, or radial zone. The number of spherical, or radial nodes, in an orbital is equal to n-l-1. One's orbital, where n is equal to 1, L is equal to 0, has no spherical node. 2's orbital, where n is equal to 2, L is equal to 0, has 1 spherical node. 2p orbital, where n is equal to 2, L is equal to 1, has no spherical node. 3p orbital, where n is equal to 3, L is equal to 1, has 1 spherical node. A plane passing through the nucleus on which the probability of finding electron is 0, is called a nodal plane. The number of nodal planes in an orbital is equal to L. For example, s-orbital, where L is equal to 0, has no nodal plane. P orbital, where L is equal to 1, has 1 nodal plane. D orbital, where L is equal to 2, has 2 nodal planes. Which of the following sets of quantum numbers are not permissible, and why? n is equal to 2, L is equal to 2, m is equal to 0, s is equal to plus 1 upon 2. N is equal to 3, L is equal to 1, m is equal to 0, s is equal to minus 1 upon 2. Solution. A. It is not permissible, as L cannot have L is equal to 2, when n is equal to 2. B. It is permissible as L cannot have L is equal to 1, when n is equal to 2. It can also have m is equal to 0. Problem 3.2. What designations are given to the following orbitals having A. n is equal to 2, L is equal to 1, B. n is equal to 1, L is equal to 0, C. n is equal to 4, L is equal to 3, D. n is equal to 3, L is equal to 2. Solution. A. When n is equal to 2, and L is equal to 1, the orbital is 2p. B. When n is equal to 1, and L is equal to 0, the orbital is 1s. C. When n is equal to 4, and L is equal to 3, the orbital is 4f. D. When n is equal to 3, and L is equal to 2, the orbital is 3d. Rules for filling electrons in orbital. 1. Electronic configuration. The distribution of electrons in various shell, subshells, and orbitals of an atom is known as its electronic configuration. 2. Generally the electronic configuration of an atom is written as an L raised to x. N is equal to shell number. L is equal to subshell. X is equal to number of electrons. For example, 3d raised to 1. 3 is equal to shell number. D is equal to subshell where L is equal to 2. 1 is equal to number of electrons. 3p2. 3 is equal to shell number, where n is equal to 3. P is equal to subshell, where L is equal to 1. 2 is equal to number of electrons. 3. Valence shell configuration. The distribution of electrons in various subshells and orbital of the outermost shell of an atom is called valence shell configuration. 4. Another method of representation of electronic configuration is pictorial. A circle or a square box is used to represent an orbital, and two arrows in the opposite directions represent two electrons with opposite spins. Two electrons in an orbital indicate that electrons are paired. Single electron in an orbitals indicates unpaired electron. Electronic configuration is mainly explained by following rules. 1. Aufbau principle. 2. Pauli's exclusion principle. 3. Hund's rule of maximum multiplicity. Aufbau principle. Aufbau is a German word, which means building up. This principle tells the sequence in which various orbitals are filled with electrons. According to Aufbau principle, in the ground state of the atoms the orbitals are filled with electrons in order of the increasing energies. Electrons enter the orbitals according to following n plus L rules. 1. Orbitals are filled in order of increasing value of n plus L. For example, consider 3d and 4s orbitals. 4, 3d, n is equal to 3, and L is equal to 2. Hence, n plus L is equal to 3 plus 2 is equal to 5. 4, 4s, n is equal to 4, and L is equal to 0. Hence, n plus L is equal to 4 plus 0 is equal to 4. As value of n plus L for 4s orbital is less than that of 3d orbital, 4s orbital is filled before 3d orbital. 2. If two orbitals have same of n plus L, then the orbital with lower value of n will be filled first. For example, consider 3d and 4p orbitals. For 3d, n is equal to 3, and L is equal to 2. Hence, n plus L is equal to 3 plus 2 is equal to 5. For 4p, n is equal to 4, and L is equal to 1. Hence, n plus L is equal to 4 plus 1 is equal to 5. Therefore, 3d orbital is filled up before 4p orbital. The order of energy of different orbitals in an atom is given below. 1s, less than 2s, less than 2p, less than 3s, less than 3p, less than 4s, less than 3d, less than 4p, less than 5s, less than 4d, less than 5p, less than 6s, less than 4f, less than 5d, and so on. The sequence given above. Pauli's exclusion principle. This principle limits the number of electrons that can occupy any orbital of an atom. Statement. Two electrons in an atom cannot have the same set of all four quantum numbers. Or, only two electrons may exist in the same orbital, with three quantum numbers same, that is, the fourth quantum number different, and these electrons must have opposite spin. Consider helium atom which has two electrons in one s orbital. The four quantum numbers for two electrons into s orbital are as follows. Table mentions electron number, quantum number, set of values of quantum numbers. In first electron number, quantum numbers are as follows: n is equal to 1, L is equal to 0, m is equal to 0, and s is equal to plus 1 upon 2. Set of values of quantum numbers 1, 0, 0, plus 1 upon 2. In second electron number, quantum numbers are as follows: n is equal to 1, L is equal to 0, m is equal to 0, and s is equal to minus 1 upon 2. Set of values of quantum numbers 1, 0, 0, minus 1 upon 2. Thus, the two electrons in the same atom have different set of quantum numbers, which is in accordance with Pauli's exclusion principle. Consider lithium atom with atomic number 3. Hence, K shell contains 2 electrons, and L shell contains 1 electron. The four quantum number for 3 electrons in lithium atom are as follows. In K shell, first electron number, quantum numbers are as follows: n is equal to 1, L is equal to 0, m is equal to 0, and s is equal to plus 1 upon 2. Set of values of quantum numbers 1, 0, 0, plus 1 upon 2. Second electron number, quantum numbers are as follows: n is equal to 1, L is equal to 0, m is equal to 0, and s is equal to minus 1 upon 2. Set of values of quantum numbers 1, 0, 0, minus 1 upon 2. In L shell, first electron number, quantum numbers are as follows: n is equal to 2, L is equal to 0, m is equal to 0, and s is equal to plus 1 upon 2. Set of values of quantum numbers 2, 0, 0, plus 1 upon 2. Thus, in an atom any 2 electrons may have the same value for any of 3 quantum numbers, but the fourth quantum number must be different. This leads to the conclusion that an orbital can accommodate maximum of 2 electrons. Hund's rule of maximum multiplicity. Statement: when several orbitals of equal energy, that is, degenerate orbitals, are available, the electrons first fill all the orbitals singly, before pairing in any of these orbitals. The configuration of 4 electrons occupying p orbitals is completely filled, or half-filled orbitals give extra stability. Anomalous behavior of copper and chromium. Atomic number of chromium is 24. Expected configuration of 24 chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. The 3d orbital is not half-filled, hence, it has less stability. Interelectronic repulsion forces 1,4s electron to enter into empty 3d orbital to make 4s, and 3d orbitals half-filled, so chromium acquires extra stability, and its configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. In this configuration, both 4s and 3d subshells are half-filled. This gives extra stability to chromium atom. Copper with atomic number 29. The expected configuration of copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. The 3d orbital is neither half-filled nor completely filled. Hence, it has less stability. Interelectronic repulsion forces 1,4s electron to enter into one half-filled 3d orbital to make it completely filled, and 4s orbital half-filled. So, copper acquires configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. In this configuration 3d subshell, incompletely filled, and 4s is half-filled. This gives extra stability to copper atom. Stability of half-filled and completely filled orbitals. Stability of completely filled and half-filled subshells can be explained on the basis of 2 factors. 1. Symmetrical distribution of electrons. The extra stability of completely filled and half-filled subshells can be explained in terms symmetry. These subshells possess symmetrical distribution of electrons. Electrons in the same subshell have equal energy, but different spatial distribution. Consequently, their shielding of one another is relatively small, and the electrons are more strongly attracted by the nucleus. 2. Exchange energy. The stabilizing effect arises whenever 2 or more electrons with the same spin are present in the degenerate orbitals of a subshell. These electrons having tendency to exchange their positions, and the energy released due to this exchange is called exchange energy. The number of exchanges that can take place is maximum when the subshell is either half-filled or completely filled. As a result, the exchange energy is maximum, and so is the stability. Possible exchange for D5 configuration is shown. Electronic configuration of elements. Observe the given table carefully. It mentions electronic configuration of the elements with atomic numbers 1 to 30.